better to speak English.
Okay, sure, better.
Okay, so he is a professor at the University of Aalto in Finland, and his areas of interest is Bayesian time series models and probabilistic machine learning methods. And his theoretical interests are stochastic process, probability in topological spaces, and Bayesian non-parametric statistics. And he also developed R packages for Bayesian time series models and generalizing Gaussian processes for non-parametric and functional analysis. And he's going to present his presentation with the title Multiple Degrees of Freedom Gaussian Processes. So you can begin now. Thank you very much.
Well, just a simple acceleration. I'm not a professor in Aalto University. I just work as a researcher there. Sorry if I did say it wrong. I work for the professor Aki Vettari. He is a professor from Aalto University. So, okay, I will present my work. My work is Multiple Degrees of Freedom of Gaussian Processes. And the general idea is this: Gaussian processes are regression. It's a popular tool for modeling. And the idea of Gaussian regression processing is to impose a non-parametric prior over the space of functions in the regression model that we're dealing with. What is the major limitation of Gaussian processes is that they're non-robust. So that means that they really have problems in the presence of outliers. So what are the solutions that you can consider so far? Well, the first one is to consider the Gaussian process regression prior, but impose a heavy tail distribution likelihood. What is the problem with that? That is really complicated to analyze. We're gonna talk about a paper that tried to perform that approximation, and it's quite hard. The second solution is, instead of use a Gaussian process prior, we can use a student T process prior. The student T processes, we can control how heavy the tail is using the degrees of freedom. The problematic that we have with student T processes is that if we have too many outliers, even the student process won't be robust enough. So we need something that is more flexible. So our idea was to assign a degrees of freedom parameter to every process, the value of the process. So for every time of the process that we are analyzing, so every time we're going to assign a degrees of freedom, and we can control that degrees of freedom, so we can control how heavy will be the tail for that time in the distribution. So what is the work structure? First, we're going to talk about some preliminary concepts to make our theoretical framework. Then we're going to present our idea of multiple degrees of freedom Gaussian process model. And finally, we're just going to see two simple examples of how this can be applied and to expand the possibilities of this new model. And finally, we're just going to talk about the conclusions. Well, first, what is a Gaussian process? If we have an stochastic process X, then it will be a Gaussian process if for every finite collection, that finite collection will be normally distributed of dimension n with a location parameter mean or a location function mu and a covariance function k, where the important thing to know is that the covariance function has to be a kernel function. And the second thing to know is that it has to be symmetric and positive defined. Notice we're going to have a lot of problems. Then, what is a Gaussian regression problem? The Gaussian regression problem is this one. If we have a collection of observational data, G and X, in this case, X will be of dimension D, and G will be the response variable of one dimension, then the Gaussian regression model can be explained like G will be equal to f of X plus a random error, where this random error will, for simplicity, say that it's normally distributed. Oh, sorry for the noise. And to f, we're going to put a Gaussian process prior, where mu f will be the mu function and k will be the kernel, symmetric kernel density function. What is the perks of using of these models? The first one is that they're analytical tractable, so that's a yay, that's a plus, because we can find an analytical solution of the posterior, we can find analytical distribution for the predictive one, and it can be computed really fast. What is the problems that we have? Again, is not robust, so it's problematic. So, well, let's try to use a student T process. In this case, this is an example of what is a Gaussian process. As you can see, the Gaussian process is fitting the curve overall, but is not performing well when we're trying to explain every observation that behaves like an outlier. It explains kind of well overall the mean, but it doesn't explain the information, particularly itself. Then let's define what is a student T process. Again, we have a stochastic process X, a collection of random variables, and it will follow a student T process if every finite collection will have a multivariate T student distribution, where V are going to be the degrees of freedom, mu is going to be the location function, and K will be, again, a symmetric kernel. What are the perks that we have right now? This kind of a student T process are more robust. You just have to control the degrees of freedom. So that's a J, that's a success. The problem is that it's analytically not tractable. So it's a problematic, but that is not a total problem at all. And the second thing is that doesn't identify outliers or don't perform dynamically well when we find outliers in the data. So what are the studies so far with the student T process? Well, the first one who proposed it was Neil in 1997. He proposed to use a student T prior. The thing is that then Ramsden and William talk about the student T prior, and he said, when he described it analytically and theoretically, he said that we will never find an analytical solution. Then Vantalo and Vettari in 2009, they use a Gaussian process regression, and they use heavy tail distribution, a student T distribution for the likelihood, and then try to fit different approximation schemes like MCMC, variational inference, and a Plax approximation to see which one we can estimate this model with heavy tail distribution better. Then it came to light. Shaw and Tang, they proposed the student T process for applications where they actually showed that if we use a hierarchical model, we can actually have the analytical computation of the posteriors, and we can do it really fast. And then Simon Sarka, Arno Soiling and Simon Sarka in 2014, in the same year, they get a paper where they provide an algorithm for fast computation of a student T process and Gaussian processes, but using a state space model formulation. So, well, of all the theoretical framework of those papers that I just mentioned so far, the most important lemma that we have to talk about is this one. This lemma is quite straightforward. It's a simple statistic, but it has a lot of implications. The full proof, you can find it in Shaw 2014. And the idea is, if we have a vector, that this vector depends on this parameter lambda, and we're going to assume that this vector has a multivariate normal distribution with parameter mean and covariance matrix K multiplied with this scalar lambda, where it's a positive random variable, such that we're going to give this inverse gamma distribution to lambda, where V, the degrees of freedom, have to be bigger than 2. So in this case, if we marginalize G towards lambda, where we're going to have the distribution that we're going to have is that G will have a T-student distribution with degrees of freedom B, location parameter mu, and covariance matrix K. Another important property that these processes or these distributions have, that's quite well known, is that if we have F, that is a student T process in general, with parameters V, degrees of freedom, mu as a mean, and K as a covariance matrix, if the degrees of freedom go to infinite, F is going to converge in distribution to a Gaussian process. So that means that we can generalize the idea of Gaussian process by student T processes, and just controlling how heavy will be the tail using the degrees of freedom. If we know that the degrees of freedom, the tail is not that heavy, we just use a really big value for V. So, well, that is a part of the student T process of Gaussian process that have been done so far. Now we're going to talk about how to generalize the idea of a student T process to multiple degrees of freedom. Well, the theory of multiple degrees of freedom is not a new idea itself. It's actually a really old one, and we're just going to adapt it to this modeling. Yeah. So, well, the first person to talk about multiple degrees of freedom in models was Selner in 1976. He proposed to do the simple regression model using multiple degrees of freedom. Then this idea was generalized by Carlin, by Chief in 1988, Carlin in 1992, and Curlin in 2012 for different models quite similar. But then Chief and Ramamurthy in 2014, they proposed for the first time like the general idea of multiple degrees of freedom for dynamic stochastic general equilibrium models, but using diagonal covariance matrix. The problem with diagonal covariance matrix, when we try to use Chief's idea for Gaussian processes, is that then we will have a Gaussian process that don't have correlation or don't have a covariance. So we're not sampling itself. And if we're trying to apply Gaussian process with diagonal matrix in time series scheme or more complicated models, if we assume that the covariance are 0, we're not sampling process. We're not assuming that there's relationship between variables. So it's not still useful. But then in 2015, Cruz proposed, extends the idea of Chip and Ramamurthy for any general covariance matrix using a normal gamma mixture. So we first, right now, we're going to talk about what is the idea of Chip-Ramamurti, present Cruz idea, and then present the general multiple degrees of freedom Gaussian processes. So well, let's assume that we have right now a random G that has a Gaussian process prior, but in this case, we're going to assume that the mean is centered at 0 and the covariance matrix will be a kernel matrix, whatever. Then we're going to extract for a Gaussian process a finite collection of random variables, let's say GQ, and GQ will have a dimension Q, and we're going to say that it will follow a multiple degrees of freedom structure proposed by Chip and Ramamurti if the covariance matrix can be written this way. In this case, the covariance matrix will be written as a diagonal, where the sigmas are the variance of every observation, and lambda are the degrees of freedom. So we can see every degrees of freedom has its own distribution with its own degrees of freedom. And in this case, we're selecting it like an inverse gamma. So what we have when we do this? When we do this, when we graph every observation conditional on the lambda will have a normal distribution. We center it at 0 and variance that way. But if we apply lemma 1 of SHA, then we will have that if we marginalize G towards lambda, we will have that G will have a T student distribution with degrees of freedom VI, location 0, and variance sigma squared. So in this case, every observation marginalized toward lambda has its own degrees of freedom. So now we have what we want. We have a generalized, but still this just works for covariance matrix. So still not solve the problem. So let's see what's the idea of Cruz, how we can adapt this idea for what we want to multiple Gaussian processes. Then we have that G follows a Gaussian process again, centered at 0. Okay, yeah, I have to get, then we get a finite collection of them. And then we're going to apply this linear transformation, where this lambda, matrix lambda will be a diagonal matrix just using the square root. Then in this case, this transformation where we transform G to zeta will have multiple degrees of freedom. Then zeta conditioned to lambda will have a multivariate normal distribution like this. And every gamma will have its own degrees of freedom. So now, if we just see every observation conditioned on lambda will have a normal distribution. But if we again apply lemma 1, we will have that every of these observations will have its own T-student distribution. So now with this idea of Cruz, we can present the idea of multiple degrees of freedom Gaussian process. Let's say that we have a collection of random variables that follow a stochastic process. F is going to follow a multiple degrees of freedom Gaussian process. If for every finite collection, we can grab his joint distribution this way, like Cruz proposed it, where in this case, zeta will have a Gaussian process centered at 0, and the collection BT and sigma T will just be independent collections of parameters, where we already know the distributions. So what are the properties of these new models that we're proposing? First, well, the problem is that we don't have an analytical solution, and it's a bit complicated to approximate. But if we just cut F marginalized on the gamma matrix, then that is a Gaussian process. But if we marginalize these lambdas over the degrees of freedom, then it will follow every one of them like a student G process. Second, if the degrees of freedom we consider the same, then this F vector will follow a student T process. So right now we overgeneralize the idea of the student T process. If one of the degrees of freedoms go to 2, then the observation in that time will have a heavy tail distribution. So we can actually identify an outlier and actually propose it and see the distribution that will dynamically change over that time. And to justify the existential of these models, like in general prior, so we can use them as a prior, we just have to, we show in our work that if something follows a multiple degrees of freedom Gaussian process, it will have also follow an implicit process regression. And implicit process regression in the paper already showed the existential of them. So with this simple transformation, looking at the transformation that this way, we can guarantee that these models or these processes are always going to exist. So now really fast, I'm going to talk about some applications. In this case, we're going to talk about these two data sets. We're going to apply our regression models, where in this case, F will follow the multiple degrees of freedom Gaussian process. And for every degrees of freedom or every lambda, we're going to give an inverse gamma distribution with 2 and 0.1. The covariance matrix that we're going to use is a simple covariance matrix, and we're just going to implement this using a Hamiltonian Monte Carlo style. These are the technical issues for the Hamiltonian Monte Carlo. For the M cycles data, this data is a measurement of head acceleration in simulated motorcycle accidents. If we can see the data is changing over time. So we really need to find something that will dynamically adjust that. We fit our model, and when we fit our model, we can see that the model, well, in this case, the model is not behaving that well as we want. But when we plot the posterior of the degrees of freedom, the expected value of the degrees of freedom, we can see that we have this time series that every time it finds an outlier, that time series goes towards 0. So it's identifying the outliers, or the posterior of the degrees of freedom are identifying the outliers dynamically. If we do the same thing for the PCI, or the price consumption index in Honduras, Honduras, the time series of PCI has 2 explosions, real explosions. So we want to identify those explosions dynamically. So we fit the model, and again, we have the same idea. We're seeing that all the observations are going oscillating, of the degrees of freedom are going oscillating around 20. And every time that this time series has an explosion, is identified in the expected value of the posterior distribution of the degrees of freedom. So far, this is what we have so far. This paper originally is just talking about the theoretical implication of this model and what are the consequences and properties that they have. So it provides a new methodology for dynamically identify outliers that generalizes Gaussian processes and studency processes, and has a lot of properties. And even so, right now we have promising results with the proposed example. We still have to do more experiments and simulations to show how it will interact for more complicated machine learning problems. So far, one of the problems that I have is that I cannot still compute the predicted distribution marginalized over the gamma matrix. So I cannot make that the predicted distributions go actually as I want, that they dynamically adjust to the outliers observations. But that is proposed in the next job. And so far, that is for me. Thank you for listening, and sorry if I talked too fast.
Thank you very much, Asael. It was very interesting. Anyone has a question? Luis?
Thank you. Yeah. I have a couple of questions for the, what is the behavior of this process when the dimension increases? Because I think you have a multiplication in the covariance structure. So have you tried with examples how the behavior is for, like, I don't know, dimension larger than 3 or 4?
Are we talking about the computational behavior when we're trying to compute this? Or
yeah,
the
what is the
behavior of the
computational
process in general?
behavior? Yeah, what is the computational behavior of this kind of processes when you increase the dimension?
Bad. Being honest, bad. Because when you increase the dimension, then it gets slower and slower.
Okay, I got it.
Yeah.
And
but for that, you can use variational inference. Variational inference don't have that problem as an approximation scheme.
Okay, okay. And the second question is, did you try other type of covariance structures besides the exponential you use in the example?
Not really. Not really. Again, the idea of this paper that I'm presenting is not about the application itself. It's just presenting a new model and what are the simple implications that they have so far. So this is our next work that we're trying to do. But yeah,
because perhaps that's the reason why you didn't get the outliers quite well in the example, because the covariance structure is exponential and it decreases very fast when you go from the center points. Yeah. So maybe that's one of the reasons, but I don't know if you try other type of covariance structure that would help. I don't know exactly.
Yeah, the other thing is that this is not a marginalized predicted distribution. So this is actually a normal distribution where I'm computing there. So that's why if I would marginalize it, solve the integral to marginalize over the degrees of freedom, then every predicted distribution by itself will be kind of similar to student T process or student T distribution. That independent of the covariance matrix that I select, even if I just select a really bad one, if I manage to solve that integral, then I will have I will adapt to the outliers better. I think it's that computationally right now I still have that problem.
Oh, okay, okay. Thank you.
Yeah, so it's not a problem of the covariance matrix, it's a problem that I'm bad at programming my own model.
Oh, I see. It's a computational problem. Okay.
Yeah.
Thank you.
Okay.
Okay, thank you. Anyone has more questions? Remember that the question can be done in English or Spanish.
Sí.
Okay. I have a question about the first simulation example. I think that the example was simulated from a real example, motorcycle,
Oh,
right?
yes.
So how can you determine the parameter you use for the simulation?
Sorry, I don't understand the question.
The parameters you used to simulate the first example.
Oh, no. This is a real data set. This is a real data set that for generating that data, they simulate the motorcycle accidents.
Ah, okay.
So no, it's not simulated data. It's real data that in the experiment to get this data, they like kind of grab a motorcycle with a robot or whatever, and they make it crash.
Ah, okay. So
Yeah,
in
yeah.
this,
So it's a simulated crash.
okay. And have you done any simulation to study the estimation of your model?
Yes, and I have done it with well, sadly didn't put it, but I just fit a curve or put a curve, and I just infected with a lot of outliers. And in this case, because I'm more trying to identify the outliers, I was just seeing the posterior predictive distribution, the posterior
Okay.
distribution of the degrees of freedom. And happens what it happens here, that every time I found an outlier, the predictive distribution would just go to 0. So I'm actually
Okay.
identifying it in the right time. Yeah.
Okay.
And that's
Thank you
also
very much.
happening because something that O'Hagan said in his papers, that with the idea of robustness in this case is that an outlier is the presence of the outlier is affecting the model itself. So I'm using that thing. And yeah, and that's why I'm putting a strong prior in that influential observation, so the prior will go toward the data.
Okay.
Yeah.
Thank you very
That was the
much.
idea.
Okay. So thank you very much. And we have right now the third